According to the National Electrical Code, specifically Section 610.14a, conductors must have an ampacity not less than that required by Part 3 of this article. Part 3 includes Table 310.16, which dictates conductor ampacities based on size and insulation type. For a number 6 American wire gauge copper conductor with XHHW insulation, the ampacity is 86 amps. Furthermore, NEC Section 610.43b states that when overload protection is provided by fuses or thermal overload devices, the fuse or thermal overload device must be rated as specified in 610.42 or b. Section 610.42 elaborates that the thermal overload device should be rated at no more than the motor's maximum operating load, as detailed in Table 430.52. This table outlines maximum operating loads for motors based on their full load currents, or FLC. For a motor with a full load current of 70 amps, the maximum operating load is 86 amps. Consequently, to comply with the NEC, a thermal overload device rated for 86 amps is necessary to protect the number 6 American wire gauge cable. While the 110 amp fuse offers branch circuit protection, it does not provide overload protection for the cable itself. Let's delve deeper into the concepts to understand the reasoning behind these requirements. Firstly, conductor ampacity is the maximum current a conductor can carry continuously under specific conditions without exceeding its temperature rating. Exceeding the ampacity can damage the insulation and potentially cause a fire. Secondly, overload protection is designed to protect the motor and conductors from excessive current draw that is sustained over a period of time. This type of overcurrent is typically caused by mechanical overload in the motor, such as a jammed hoist or excessive weight. Thirdly, branch circuit protection is intended to protect the entire branch circuit from short circuits and ground faults. These faults cause very high currents to flow, which can quickly damage equipment and cause fires. A fuse or circuit breaker provides this protection by interrupting the circuit when a fault occurs. The NEC distinguishes between overload protection and branch circuit protection because they serve different purposes and respond to different types of overcurrent. Overload protection is sized to protect the motor and conductors from sustained overcurrents, while branch circuit protection is sized to protect the entire circuit from short circuits and ground faults. In the case of a Hoist motor, the number 6 American wire gauge conductors must be protected from overloads, even if the branch circuit protection is provided by a larger fuse or circuit breaker. This is because the number 6 American wire gauge conductors have a limited ampacity, and exceeding that ampacity can damage the conductors and create a fire hazard. The thermal overload device, rated for 86 amps, provides this overload protection by tripping and disconnecting the motor from the circuit if the current draw exceeds 86 amps for a prolonged period. The 110 amp fuse provides branch circuit protection by tripping and disconnecting the entire circuit if a short circuit or ground fault occurs. In summary, the NEC requires both overload protection and branch circuit protection for hoist motors to ensure the safety of the equipment and the electrical system. The overload protection, provided by the thermal overload device, protects the motor and conductors from sustained overcurrents, while the branch circuit protection provided by the fuse protects the entire circuit from short circuits and ground faults. To further clarify, let's consider the scenario if the overcurrent device was not rated for 86 amps or less. Firstly, if the overcurrent device was rated higher than 86 amps, the number 6 American wire gauge conductors could be subjected to sustained overcurrents exceeding their ampacity. This could cause the conductors to overheat, damaging their insulation and potentially leading to a fire. Secondly, if the overcurrent device was omitted altogether, the number 6 American wire gauge conductors would be completely unprotected from overloads. This would significantly increase the risk of conductor damage and fire. The NEC requirements for hoist motor overcurrent protection are based on sound engineering principles and extensive testing. These requirements are designed to ensure the safe and reliable operation of hoist motors and electrical systems. It is important to follow these requirements carefully to prevent electrical hazards and ensure the safety of personnel and property. Let's consider some additional factors that may influence the selection of overcurrent protection for hoist motors. One factor is the motor's service factor. The service factor is a multiplier that indicates how much overload the motor can handle for short periods. Motors with the highest service factor can typically tolerate higher overcurrents for short durations without overheating. Another factor is the ambient temperature. The ampacity of conductors decreases as the ambient temperature increases. Therefore, it is important to consider the ambient temperature when selecting the size of conductors and overcurrent protection devices. The NEC provides tables that denote the ampacity of conductors based on ambient temperature. Another consideration is the type of load being lifted by the hoist motor. Some loads may be more prone to causing overloads than others. For example, lifting a heavy, unbalanced load may place more stress on the motor and increase the risk of overload. In these cases, it may be necessary to use a more conservative overcurrent protection strategy. It is also important to ensure that the overcurrent protection devices are properly installed and maintained. Fuses should be replaced with the correct type and rating. Circuit breakers should be tested periodically to ensure that they are functioning properly. Regular inspections of the electrical system can help identify potential problems before they lead to overcurrent events. In conclusion, proper overcurrent protection is essential for the safe and reliable operation of Hoist motors. The NEC provides specific requirements for overcurrent protection that must be followed to prevent electrical hazards. These requirements take into account the ampacity of the conductors, the motor's full load current, the service factor, the ambient temperature, and the type of load being lifted. By carefully considering these factors and following the NEC requirements, it is possible to ensure that hoist motors are adequately protected from overcurrents. Keep in mind that electrical codes and standards are subject to change. Always consult the latest edition of the National Electrical Code and other relevant standards for the most up-to-date information. It is also advisable to consult with a qualified electrical engineer or electrician to ensure that your electrical system complies with all applicable requirements. Furthermore, consider the specific application of the hoist motor. For example, a hoist motor used in a critical application, such as lifting people, may require a more robust overcurrent protection system than a hoist motor used in a less critical application. In critical applications, it may be necessary to use redundant overcurrent protection devices or to implement other safety measures to ensure that the motor is protected from overcurrents. Always consider the potential consequences of a motor failure when designing the overcurrent protection system. A motor failure can not only damage the motor itself, but can also cause other equipment to fail or create a safety hazard. By taking a proactive approach to overcurrent protection, it is possible to minimize the risk of motor failures and ensure the safe and reliable operation of your electrical system. Also, remember to properly label all overcurrent protection devices. The label should clearly indicate the type and rating of the device, as well as the equipment that it protects. This will help to ensure that the correct overcurrent protection device is used and that it is properly maintained. Another important consideration is coordination of overcurrent protection devices. Coordination refers to the selective tripping of overcurrent protection devices in a circuit. The goal of coordination is to ensure that only the overcurrent protection device closest to the fault trips, while other overcurrent protection devices upstream remain closed. This minimizes the impact of the fault and allows the rest of the electrical system to continue operating. Coordination is typically achieved by selecting overcurrent protection devices with different time current characteristics. The time current characteristic of an overcurrent protection device is a graph that shows the amount of time it takes for the device to trip at different current levels. By selecting overcurrent protection devices with appropriate time current characteristics, it is possible to achieve coordination and minimize the impact of faults. Another technique that can be used to improve overcurrent protection is the use of ground fault protection. Ground fault protection is designed to detect and interrupt ground faults, which are faults that occur when current flows from a live conductor to ground. Ground faults can be dangerous because they can cause electric shock and fires. Ground fault protection is typically provided by ground fault circuit interrupter, or GFCI. GFCIs are required in many locations, such as bathrooms and kitchens, to protect people from electric shock. In industrial applications, ground fault protection may be provided by a ground fault relay. Ground fault relays are used to detect ground faults and trip a circuit breaker to interrupt the circuit. In addition to the technical aspects of overcurrent protection, it is also important to consider the human factors. People who work with electrical equipment should be trained on the hazards of overcurrents and the proper procedures for working safely with electrical equipment. Training should cover topics such as how to identify potential overcurrent hazards, how to use personal protective equipment, and how to respond to overcurrent events. It is also important to have clear and concise operating procedures for electrical equipment. The operating procedures should specify the steps that must be taken to safely operate the equipment and the actions that must be taken in the event of an overcurrent. By addressing both the technical and human factors of overcurrent protection, it is possible to create a safe and reliable electrical system. Let's summarize the key takeaways. Firstly, always consult the latest edition of the National Electrical Code and other relevant standards for the most up-to-date information. Secondly, select overcurrent protection devices that are appropriate for the application and that comply with all applicable requirements. Thirdly, ensure that overcurrent protection devices are properly installed, maintained, and labeled. Fourthly, coordinate overcurrent protection devices to minimize the impact of faults. Fifthly, consider the use of ground fault protection to protect people from electric shock and fires. Sixthly, train people on the hazards of overcurrents and the proper procedures for working safely with electrical equipment. Lastly, have clear and concise operating procedures for electrical equipment. By following these guidelines, it is possible to ensure that your electrical system is adequately protected from overcurrents and that it operates safely and reliably. Also, remember to consider the long-term reliability of the overcurrent protection system. Overcurrent protection devices should be inspected and tested periodically to ensure that they are functioning properly. Fuses should be replaced with the correct type and rating. Circuit breakers should be tested to verify that they trip at the correct current level. Regular maintenance of the overcurrent protection system can help to prevent failures and ensure that the system is ready to respond to an overcurrent event. In addition to routine maintenance, it is also important to upgrade the overcurrent protection system as needed. As electrical loads change or new equipment is added, the overcurrent protection system may need to be modified to accommodate the changes. For example, if a new motor is added to a circuit, the circuit breaker may need to be replaced with a larger breaker to provide adequate overcurrent protection. It is important to consult with a qualified electrical engineer or electrician to determine if the overcurrent protection system needs to be upgraded. Furthermore, consider the impact of overcurrent events on other equipment in the electrical system. Overcurrent events can cause voltage dips and surges that can damage sensitive electronic equipment. In some cases, it may be necessary to install surge protection devices to protect equipment from voltage surges caused by overcurrent events. Surge protection devices are designed to divert excess voltage away from sensitive equipment, preventing damage. In conclusion, overcurrent protection is a critical aspect of electrical safety. By carefully considering the various factors that influence overcurrent protection and by following the guidelines outlined in this discussion, it is possible to create a safe, reliable, and well-maintained electrical system. Remember to always consult with qualified professionals and adhere to the latest codes and standards to ensure the safety of personnel and property.